Okay. Ladies and gentlemen, let's we're gonna have to move kind of quick, so are you guys engaged? Are you listening? All right. We're gonna have to move kind of quick because I'd like to finish these notes up today because we're a little bit behind the other classes. Well, it's just because of my computer malfunctions. You know what I mean? Yesterday we learned that a triangle, if you add up all the interior angles, what does it add up to? 180. 180. We did that little activity, didn't we? Well, this first blank here is diagonals. And what they're getting at is the fact that if you draw diagonals from one of the vertices of a polygon, you will split up any polygon into what kind of shapes? Triangles. And then what you can do is you can say, well, since the sum of the interior angles of a single triangle is 180, you can count how many triangles there are and multiply it by 180 to get the sum of the interior angles of any polygon. But here's the thing, it's got to be a convex polygon. What does that mean? It's not a star. There's no dents. You guys with me on that? There's no dents. All right. Well, and so this chart here, it says a number of sides, 3, 4, 5, 6, n. Are you guys with me on that?
Yeah.
And what they're going to want you to do is they're going to want you to write down how many triangles are in each of these shapes. And how you find that out is by drawing what? The diagonals, okay, from one of the vertex. So for a triangle, let's draw a triangle real quick. Can a triangle have any diagonals? No, because if you try to connect other endpoints, you just get sides, don't you? So how many triangles are in a triangle? One. And we learned yesterday that if you add all those interior angles together, it's 180. You guys with me so far?
Yep.
If you've got a quadrilateral, pick a vertex and draw a diagonal. How many triangles do we have? 2. 2 times 180 is 360. Don't we have 5 sides here? We do. How many triangles?
3.
3 times 180?
540.
540. If we had a 6-sided shape, we drew all the diagonals from one vertex. How many triangles do you have? 4. 4 times 180? Okay, so basically we don't want to have to draw all the pictures out every time to figure these out. So we're going to figure out the relationship here. The number of sides, how do you go from the number of sides to the number of triangles? What are you doing each time?
Subtracting 2.
Subtracting 2. And then what are we doing to go from the number of triangles to the sum of the interior angles? So it turns out there's a formula you can use, and it's n minus 2 times 180. If you know the number of sides you have, you're going to subtract 2 from it and multiply by 180 to get the sum of your interior angles. So basically that's what theorem 8.1 is. Theorem 8.1 is the polygon interior angles theorem. It says that the sum of the measures of the interior angles of a convex n-gon is n minus 2 times 180 degrees. Now, a corollary is something that's easily proven from a theorem. So the corollary to theorem 8.1 is the interior angles of a quadrilateral. What did we learn that the sum of the interior angles of a quadrilateral? There we go. What did they add up to?
360.
And that's just basically something that they want you to commit to memory and not have to do n minus 2 times 180 all the time. Just remember that if you've got a quadrilateral, it's 360 degrees. That's the only point of that corollary, is so that you remember that a quadrilateral, the sum is 360. Okay, how are you guys feeling so far?
Good.
If I'm going too fast, just say so. If you need something clarified, just say so. Well, let's flip this over. Let's use this a little bit, shall we? Example 3 says find the sum of the interior angles of a convex octagon. Well, I'm not going to draw a picture because I think I know what to do. Octagon has how many sides? 8. So the formula goes 8 minus 2 times what?
180.
180. Let's see what we get. I got, yeah, 1080 degrees. 1080 degrees. That is the sum of the interior angles of a convex octagon. Aren't you proud?
Yes.
Example 4. It says find the measure of an interior angle of a regular convex dodecagon. Dodecagon is a 12-sided figure. Does anybody have a kind of a plan for this?
12 minus 2
12 minus 2
times
180.
times the 180, okay?
Divide that by the number of triangles.
Well,
Or just
maybe.
by the side.
Well, because it's a regular dodecagon, we know all the angles are the same. And they're wanting us to find the measure of one of them. So once we get our total, what are we going to do? Divide by 12. Divide by 12. I think we got a plan. Let's do it. I love it when a plan comes together. That's, I think it's from the 18, actually. So this is the sum, but then to find each one, what do we do?
Divide by 12.
Divide by 12.
Divide by 12.
150.
150 degrees is the measure of one of them. Very good, very good. Why don't you all try number 5 for me? And I'll take roll and I'll come around and check and see how you did. I'd walk around and see how everybody did and kind of check on every single person. But because we have some notes to get through, I'm gonna go ahead and work it out myself, but I'm gonna be quiet, and then we'll check and see if we agree. If you had a chance to finish it, go ahead and take a look, see if we agree. As I'm walking around, if you don't agree, let me know. Tell me what's up. Okay, so you assume that it is a regular pentagon, and you divide it by 5? Not so. Instead, we're given equal measures. Yep.
So can I just combine all those and just do that and then that minus that?
Yeah. I like giving the thumbs up like a whip. Fun. Also, I thought it had a bit of a Western thing, you know? Are you guys good? Is everybody good? You're trying to get that stuff, so.
Yeah.
So I would need to subtract the 540, subtract the 386. All right. Connor, you good?
Yeah.
Sweet. So, is everybody good on example 5?
Pretty sure.
Yeah.
Now, this is a good time to reinforce something here. Any pictures that are drawn by me or the teacher that taught this before cannot be assumed to be to scale. Are you guys with me on that?
Yeah.
It's actually really difficult to draw things to scale quickly. And so for these examples, basically what I'm getting at, does X look anywhere near 154 degrees?
No.
It doesn't, but we gotta trust the relationships that we're given. In truth, to make this more accurate, the shape would probably look more like that. You guys with me?
Mm-hmm.
Yeah. All right, example 6. If the sum of the measures of the interior angles of a convex polygon are 2,340 degrees, classify the polygon by the number of sides it has. So we're still going to use that formula that we derived, right? We're still going to use that, but we're kind of working backwards. We don't know how many sides, but we know that the relationship is n minus 2 times 180. And that our total, our sum of the interior angles is what value?
2,340.
2,340. So I would suggest dividing by 180. I suppose you could distribute it, but that seems like extra work. What do you get when you divide it?
13.
Oh,
15.
Yeah.
Oh. What do you divide by 13?
Wait, is it 13?
Yeah, it's 13.
Yeah. Oh. Sorry, I have to plug it in now. It's a trick question. Yeah, 13. And then what do you do to get n by itself?
Add 2.
So how many sides are we talking?
15.
15 sides. And if that had a name, we would go ahead and give the name, but I don't think we learned a 15-sided one.
15 are
So
gone.
let's call it
15 gone.
And it's actually just 15 gone.
Yeah.
Isn't that strange? 15 gone. Okay, so so far we've dealt with the sum of the interior angles of a polygon. Well, now we're going to switch gears. And instead of focusing on the interior angles, we're going to focus on the exterior angles. So let's, before I tell, well, it says what it is down here, kind of gives it away. But before I explain it, will you guys draw a pentagon in here? That's kind of messy. Let me clean that up a little bit. I don't like that at all. That's like a Superman symbol. Are you guys familiar with a guy named Michael Jordan?
Space Jam guy.
For Space Jam, yeah, okay. Well, there's also this guy named Dominic Wilkins, and when I was a little kid, those were like the basketball studs. I mean, there's a few others, but Dominic Wilkins and Michael Jordan, they both could do a 360 dunk with relative ease. What does that mean to do a 360 dunk? Yeah, so they're full in the air, they're fully rotating their body all the way around and dunking. Well, why do they call it a 360 dunk? Because you can measure rotation in degrees. And if you rotate all the way around, that's 360 degrees. You guys with me on that?
Yeah.
Well, that helps me to remember the polygon exterior angles thing. First things first, exterior angles are created when you extend the sides of a polygon out. Now, when that happens, you're always going to have a straight angle. The exterior angle is the non-straight angle right there. Now you just as easily could have extended this one out that way, but we're going to be kind of consistent with how we do it. And we're going to always extend them clockwise, I'll say. So to make the exterior angle here, we'll extend that out. To make angle 2, extend that out. To make angle 3, extend that out. To make angle 4. And finally, extend that out to make angle 5. And what's interesting about this is if we had decided to go the other way with it, the angle measures would still be exactly the same. Okay, it's kind of curious. But it's more customary to have them all kind of fanning out in the same direction. Now the reason why Michael Jordan and Dominic Wilkins remind me of this theorem is because think about if you're walking along this side right here. So you're walking along, and then when you hit this vertex, don't you have to turn to stay on the polygon?
Yeah.
So you turn once. Oh, you get to this one, you gotta turn again. You turn again, you turn again, you turn again. You come up here, and you're finally back where you were. You've gone in a big what?
Circle.
You've gone in a big circle. So that right there is why the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360 degrees. Because you're going around in a circle, which is 360. How do you guys feel about that?
Pretty good.
Pretty good? Now what's curious about this is it doesn't matter how many sides you have. If you have a triangle, you can draw this out real quick. If you have a triangle and you draw the exterior angles, you're still going to end up going in a what? In a circle. You start this way, you go this way, you go this way, and then you end up back where you were. That's 360 degrees. No matter how many sides it has, what are they all going to add up to? Now, you might be thinking, well, but what if you have like 700 sides? Which is possible. Well, if you have 700 sides, each exterior angle is going to be a fraction of a degree. You guys with me on that? They're all going to be super tiny because they'll be tiny little turns until you finally get around. All right, let's flip it over, see what's going on. Example 7, what is the value of x in the diagram? Well, what kind of angles are we looking at here? External angles. What do they all add up to?
60.
360. It's a little bit easier, isn't it, than the other one?
Yeah.
Cleaned it up a little bit. It's 128. Some days I'm really good at doing math in my head. Other days don't sit on. Oh, I think I forgot to.
I got 228.
Oh, yes. I concur. Yep. Hey, I was only off by 100.
Only 100.
Yeah.
Small difference.
And then what do you do to solve this?
Subtract.
Subtract and divide by 2. And you get
130.
oh,
66.
I got 66.
I do as well. 66. And you could write 66 degrees because x is an angle measure, isn't it?
Yeah.
Also, it's possible to get fractions, okay? Just a heads up. You could have like 66 and a half degrees or a third or whatever. So fractions are possible here. All right. Well, our last example. Good job, team. We're going to make it. Our last example is a stop sign.
Stop shot.
A stop sign. And a stop sign is shaped like a regular octagon. If it's regular, what do we know about all the sides and angles?
They're all equal.
They're all the sides are congruent, all the angles are congruent. It says to find A, the measure of each interior angle, and B, the measure of each exterior angle. I don't feel like I need to draw a picture here. I feel like I've got a good handle on what they're talking about. But what are you going to do to find the measure of each interior angle?
8 minus 2 times 180.
8 minus 2 times 180. That will get you the sum of them. And then what are you going to have to do to get the measure of one of the angles? Divide by 8. Why will that work? Because it's regular, and each one's going to be the same, isn't it? What about for part B? How are you going to find the measure of each exterior angle? Well, what do they all need to add up to?
360.
360. And then guess what? Find the measure of one of them. Divide by 8. Yeah. Go ahead and give these a shot. So please double check your answers, make sure you feel squared away. And if you do, I would recommend to go ahead and do a little bit of practice, page 510. Yeah, because this is chapter 8. So page 510, numbers 1 through 21, and then jump over to 25 through 31. And I'm going to make the assignment all. But here's the thing. Are you ever mandated to do all the problems?
Yes.
So if you want to do the odds, you can. I just don't know if that's enough practice. You know what I mean?
Yeah.
You could, but that's always a risk that you take. Yeah. So if you don't mind, go ahead and get started on this. That'd be great.